Broadcasting live from Traverse City, Michigan, this is the Progressive Technology Hour, and I'm your host, Bill Alek. Just to give you a little background about myself, I'm a degreed electrical engineer, and I currently do software consulting work for major corporations. That describes my day job. At night, I become Dr. Houdini, researcher, explorer, and experimenter in the world of exotic technologies. What are exotic technologies? Well, this includes such areas as free energy, gravity, anti-gravity control, the study of nature of time and time travel. We'll explore not only the technology, but also the how-to part of the technology. So let's have some fun today and explore the world of exotic technologies. Folks, my special guest today is scalar wave researcher, Professor Dr. Konstantin Meyl. Dr. Meyl teaches the subject of power electronics and alternative energy technology at the University of Applied Sciences in Furtwangen. Being a 15-year-old pupil, he already carried out the first measurements on eddy current breaks. His dissertation at the Technical University of Munich, 1979, as well as his doctoral thesis at the University of Stuttgart, 1984, were dedicated to the three-dimensional calculation of eddy currents. His book, Scalar Waves, and other publications are available for download at www.mininova.org/tor/108251. Now you can go to Achieve Radio's website and download this information on scalar waves. Now, scalar wave technology for the experimenter is also available on my website. Just go to my webpage at www.intellect.com/index/projects/smartlink/scalar wave technology experimental kit 2003. And again, that's on my webpage at SmartLink. Professor Meyl, welcome to the show.
Hello, Alek.
Professor, would you please tell the listening audience what are scalar waves?
Well, scalar waves are very old. They have different properties compared with the electromagnetic waves, which are well known, but scalar waves are not as well known as electromagnetic waves. Some physicists have problems with these waves, which propagate in a longitudinal way, and not as a transverse wave like the electromagnetic waves. And they have problems because they have learned that scalar means they have no direction, but waves always have a direction. They are propagating in one direction, and as a vector, you see. And this makes problems, but you need to know that this name is very old, and I'm not the founder of the name, so I only can explain how it happens that this expression was used. It's because it originates in mathematics, and it's as old as the wave equation, which goes back on the mathematical Laplace. Perhaps you know, Laplace is a very well-known scientist. He had been, and he founded the wave equation. And the wave equation may be separated in two parts. One part is describing transverse waves, which are the electromagnetic waves, the light perhaps, and the radio waves, which we are using now. And on the other hand, we have a second part, which is describing a scalar wave. A scalar wave, that means we have particles or, special vortices which have forms just like a particle. And these are forming a standing wave just like the sound wave. The sound wave is a special form of a scalar wave because one air particle is pushing the next, and this is forming a standing wave. The same we have with gravitational waves or plasma waves. These are other forms of scalar waves.
Mm-hmm. Now, this sort of scalar wave, is it related? Is it a type of mass fluctuation, or how would you describe it?
Well, you see, the electromagnetic wave is a transverse wave. That means the field pointers are perpendicular to the direction of propagation. Okay. And another possibility is that the wave propagates just in the direction of one field pointer. That means in the direction of the electric field pointer or of the magnetic field pointer. And then we have an electric scalar wave or a magnetic scalar wave. Mm-hmm. Tesla always has used the electric scalar wave. You need to know that we have three waves. Electric scalar wave, which is propagating into the direction of the electric field pointer, the magnetic scalar wave, which is propagating in the direction of the magnetic field pointer, and the electromagnetic wave, which is propagating perpendicular to both.
Okay. Now, question. Now, is the scalar wave, is it something like a pointing vector? Is there a relationship between a pointing vector and a scalar wave? Or is this something different?
Yes, you see that we have a problem if we want to describe an energy distribution or energy carrying by a wave. Because the electromagnetic wave, you know that the field pointer of the electric field is 0 at the same point as the field pointer of the magnetic field is 0. So that is in the far field of an electromagnetic wave antenna, you see. Then if both are 0, you have problems to explain where the energy is.
Okay.
And this is why you need a trick, I would say, how to explain the energy, and this is why we are using the pointing vector. With a scalar wave, we don't have this problem because there is the angle between electric and magnetic field pointer is not 0, but is 90 degrees. And if it is 90 degrees, at the point where the electric field pointer is 0, the magnetic has its maximum, and vice versa. You see, that means you never have the situation that both are 0, and this is why the scalar wave always is able to transport energy, while the electromagnetic field has not this property.
I see. Mm-hmm. Okay. Okay, well, so now the energy that's being transported in the wave is now carried in the scalar component. Is that how the calculations work out?
Yes. You see, it's not even wrong what you say. It's a bit more complicated. But let's try to explain it to everybody so everybody will understand it. Is that you have both waves in the wave equation explained, and both do exist. So you always have the chance to use the one part which is transporting energy, or the other part which is maybe used for information, transmission. So we have both parts, you see, and it's up to our antenna which part will be maximized, and which one we want to use, you see.
Okay.
And we, if we calculate the scalar wave part, which is the longitudinal wave part, if we calculate this for a standard antenna, then we calculate with the speed of light, and then we get the result that this wave has nearly no energy any longer if the distance is longer than, let me say, the wavelength divided by 2p. That's about a sixth part of the wavelength. It's not very far. This is what we are using now with RFID systems, you know.
Oh, okay.
And this is as well what the MIT is using, because they are propagating wireless energy transmission as well, and they are using the magnetic part.
Uh-huh.
Mm-hmm.
Now, you developed some technology a few years ago based on Tesla's technology here, and you assembled this in a kit.
Mm-hmm.
Now, is this available commercially, or how do you go about selling this?
Yes, you see, it was a long way till we reached this point. First, I have pointed out that the Maxwell field equations, which are the basis of electromagnetism,
right.
They put these scalar parts, these scalar wave parts in the wave equation to zero, because, well, if you describe it in a mathematically way, this is the divergence of the electric field pointer. They put it to zero and say this is zero, and then we have no scalar wave parts anymore. And because the divergence of a field pointer is a scalar part in the wave equation, and this sounds why we call it a scalar wave, you see. As Maxwell equations do not describe it any longer, but I have to explain that the original Maxwell equations described by quaternions, the original equations did describe scalar waves, but when Maxwell dies, the new mathematical description by Professor Gibbs was the one we are using today in vector analysis, and this description, when this was used, they changed the original Maxwell description into the one we are using today in textbooks. Mm-hmm. And this description is without scalar waves, because there had been this quarrel, this fight between Heinrich Hertz on the one side, the founder of the electromagnetic wave, who has shown that this wave exists, the first, and on the other hand, Nikola Tesla, who has shown experiments that the scalar wave is existing. Yes. And this fight was very heavy because everybody said he was right. Hertz said, and his participants said he is right, and Tesla said no, he's wrong, I'm right. So at the end, now I know that both were right, because in the wave equation you have both solutions. But at that time, they said only the Hertzian wave is proved, and we only want to use this wave, and this is why we put the other one to zero.
Okay.
That is the problem we still have today. That if you put the wave to zero you want to use, then you can't use it any longer. You can't. You are not able to construct a measurement equipment to measure this wave. So this is the situation.
Now, is there any test equipment available that can measure the scalar wave?
Yes, you see, we had just this problem at that time, and I have shown that if you expand the Maxwell theory, then you are able to bring back these lost parts of the scalar waves back into the field description. And this expanded theory I have developed and I have published in my books and in a lot of papers. These expanded theory is the basis, and I wanted to show that this theory is right, and that's why I have developed equipment, a device, just to show that it is right, and that was the point when I started the experiments to repeat the experiments of Tesla. Mm-hmm. Because Tesla has shown that scalar waves do exist. It is the Tesla radiation, it's called Tesla radiation, and that was now about 10 years ago. 18 years ago I started with my theory, and 10 years ago I started with these experiments, and I could show that these experiments prove that scalar waves exist. Mm-hmm. And that was a very, very important step, I think. And but you know that there are a lot of people who ignore everything and who deny it because they have learned that Maxwell equations do not describe scalar waves, and that's why scalar waves may not exist, and you have no measurement equipment to prove it, and therefore this is the reason why scalar waves may not exist, because you can't prove it. Okay, mm-hmm. And this was why I had to show to my colleagues, the scientists all over the world, that Tesla was right. Mm-hmm. And by this I developed this experimental set, and this is in the roots. It is reproduction of the Tesla experiment, which is now 100 years ago. Okay, now to bring I know your question, Alex. I know your question. You said, okay, are you able to measure it? Yes, I have not forgotten it. And you see, this experiment shows not only that these scalar waves exist, but you need a transmitter and a receiver, and the receiver is, if you want, a measurement equipment for the transmitted scalar waves. Okay. So I can say, yes, we are able. But we are able only to measure what we have transmitted. We have no measurement equipment which is able to measure the whole range, which could be possible. Okay, now Tesla came up with this patent for this special transformer, and what you were able to do in your experimental kit here is that you took this special transformer and you laid it out on a printed circuit board. It's a spiral transformer, right? Mm-hmm. Now Tesla's original patent shows a spiral transformer, but he doesn't really give any kind of dimensions on it at all. You know, the size, and any kind of parameters required for fabricating this coil. And I don't know, maybe you can just use ordinary household wire to fabricate this coil? I was just wondering what you originally did you originally experiment with these flat coils in your experiments, or? Yes, I started my research and my developments with producing these pancake coils, these Tesla coils, and I used different material. I was using high-frequency cables, and now we reproduce the experiment with standard layers because it's easier to produce a reproducible device. And you see, in science, it is necessary that an experiment is reproducible wherever and whenever you want. And so we are using now these Tesla coils in a printed way because this is very, very easy, reproducible, and we are very successful with this equipment.
Uh-huh.
You need to know that we have sold this experimental set all over the world, to not only to America, but as well to Canada, to Australia, to New Zealand, to China. The Technical University of China of Peking has bought one, and one is in Moscow and in St. Petersburg, in Warsaw, and all over in Europe. And they all could reproduce these experiments and these effects because they want to know whether scalar waves do exist or not, because it's a very old fight.
Mm-hmm. Now, I talked with some other researchers, regarding the design of this coil, and for people who want to look up this patent, this original Nikola Tesla patent. The title of its coil for electromagnets, and it's patent number 512340, and it's dated January 9th, 1894. And it shows a couple of designs here for his flat coil. Now, the theory behind this is that as current passes through this coil, you have something very similar to an asymmetric magnetic field. And maybe this has something to do with bringing out or exposing the scalar component of this wave that's connected to this electromagnetic wave. Would you agree with that explanation? That we're creating an asymmetric magnetic field here, and we see the scalar component emerging?
Not at all. Not at all. You see, I have a very different opinion, and the Tesla description is really not very useful. I know Tesla has had the same problem like we have nowadays. If you are writing a patent, if you write something which is contradict to the mainstream theory, then you don't get any patent. And you need to write something which is in the theory or in the idea of the inventor is nonsense, but it is what the patent office wants to hear, to listen to. And this is why I found out. I read all these Tesla books and what is published by the Tesla Society and the Colorado Spring Notes and so on. You see that you find a lot of information inside, but at the point where it could be interesting, there stands that you have to use the coil number 8, but nobody knows what the coil number 8 was, because it was his description. He knows what he uses, but nowadays it is nearly impossible to reproduce what he has done exactly one-to-one, you see. This is why you have to find out what his ideas were. And I think I have found out what his ideas were. And you see, this Tesla coil is part of an air transformer. And this air transformer inducted from one coil to the next, to the Tesla coil, currents. That means that the electrons were moving in, with a high frequency of the primary coil. But if you if you are using a flat coil, then the line is shorter if you come to the center of this coil. You understand what I'd say? That means that the moving energy is getting less, and on the plates, the rotating energy is coming and is used. And if you turn a ball very, very quick, then it becomes flat and it becomes a ring, something like a ring vortex. And now you need to know that I'm able to calculate all particles in quantum physics. I have published it in my book. So I describe them and I calculate the particles as being vortices, field vortices. And if you are using my extended field theory, you are able to measure and to calculate what no quantum physicist is able to calculate till now. Because they have no chance to calculate the particles, but I can if I'm using these vortex theory. And if you are using my model, that a particle as well the electron is a ball vortex, then if you turn it very quick, you get a ring vortex, and this ring vortex is not moving any longer through the cable, but all around the cable. And this means that you have no longer losses, because you have no losses. You get the losses, the copper losses, because of the electron running through a cable and always pushing from one edge to the next. You see, bang, 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 and that gives the resistance. And if you have no resistance, then you have no losses. And this is, I think, one very important idea behind the Tesla experiments. That he is producing or changing electrons into ring electrons, which he is spreading through the air and which are forming a scalar wave, because a ring vortex is a scalar particle, just like an air particle, which is forming a sound wave.
So, Professor, just looking at this Tesla design here, I'm looking at his patent, and again, for people on the internet, you can go to my website. Look under Smart Link, and I have a copy of Nikola Tesla's patent, this flat coil design, and it's patent number 512340. And just to sum up what you're talking about here is that this flat coil is either simulating or maybe emulating a macro particle.
Yes, that's right.
It's a very rough analogy, but it seems like electromagnetically we're perhaps creating a macro particle here.
Well, it has as well to do with the voltage. Tesla was using high tension, and he, if you know the book of Cheney of bibliography of Tesla, Cheney has written. You know this book? It's very famous.
No,
Man Out of Time is the title. Man Out of Time. Cheney has written.
The title does sound familiar.
Yeah.
What is it again? Man Out of Time?
Man Out of Time. It's a very famous book. I think the most famous book about Nikola Tesla.
Ah, okay. Yes, I've heard of that book.
Written by a journalist or something, I guess. I think she's a journalist. And this, on the front page, there is shown Tesla with a coil, and you are able to see that the coil winding differs at a special point. And this point Tesla has measured, and he has found out that when the voltage has reached 511,000 volt, then at that point you get a lot of lightning, and that means you get losses. And this is the point when the electron comes out of the wire and is running all around the wire. And you are able to see that he is changing the winding. The distance between one winding to the next is much bigger from this point on.
Uh-huh.
So this proves what he has done, that he has found out that this called electron voltage, I think you call it in that way as well, this is the tension when the electron decays and gives light, and you have losses because you have no electron anymore, you see.
Uh-huh.
And this is why our high voltage cable are working with maximum 380,000 volts and no more.
Uh-huh.
Yeah.
Now, is there a photo? You mentioned that there was a photo showing this coil?
Yes. Well, if you don't know the book, I have it only in German, but I think the cover is the same in English. I would have to scan the photo and send it to you if you want, if you're interested in. But I think this proves that what happens in the Tesla coil, and I wanted to reproduce this, but I had problems to reach these high voltage because I have not the laboratory to do this. And this was the reason why I tried to find out what the properties are if I have a small voltage. And my experiment is working only at maximum 10 volt, no more.
Okay.
So, but I'm able to show that the properties may be proved as well.
Okay. Now I just Googled this title here, Man Out of Time, and it is available from Amazon.com. So the audience out there that's interested in ordering this book, it is available from Amazon.com.
Well, you have to pay attention a bit because this book is forming a nice picture of Tesla, but this is not Tesla at all, because you need to be a physicist to understand Tesla better. And the author is not a physicist. She is a, book writer.
Right. Okay, well, this book is available online. And at the moment, I'm looking through it here.
Okay.
Okay, so have you done any work with the conical coils?
Which coils?
Conical. There's some kits that are available. I think from Edmund Scientific makes a high voltage Tesla coil, and these are the cone-shaped coils. I was wondering have you done any work with that at all, or no?
No, I did not work with high voltages, but because I found out that it is not necessary to reproduce the effects. 10 volt is enough just to show that this scalar wave is not propagating with speed of light, but it's propagating quicker. With my test set, I show that it is propagating with about 1.5 times the speed of light.
Oh, 1.5, huh?
Yes. It is very easy to measure because you need to realize the frequency, which you see on the frequency counter, and you have to measure the wavelength, which is you found if you measure from one knot to the next. And because it's a standing wave, and you are able to find these knots. And I ran with my students over the field in front of the university, and we tried to find the knots. And so a lot of people did this. And if you multiply the wavelength with the frequency, then you have the speed of propagation. And this normally is the speed of light, but in this time not, you see.
And in your calculations, you came up with 1.5 times the speed of light then.
Mm-hmm.
Oh, that's very interesting.
And you need to know that it is not a phase speed, but the speed of the group. Einstein said that, or up to Einstein's theory of relativity, the speed of the phase angle may be quicker than speed of light, but this is not transporting energy, and only the speed of the group is transporting energy, and this is not allowed to be quicker than speed of light, and this is the problem. Well, it's a problem to standard physics. It's not a problem to me, because if you measure this, then you have the proof. And I think the measurement is showing the truth and not a wrong theory and a wrong model.
Mm-hmm. Now, do you think the scalar wave component, if it's propagating at a different speed than the speed of light, then you can say that it's not really connected to the transverse wave component?
That's right. That's what we call noise, because we are not able to measure the scalar wave directly, but indirectly. And please use my model that a transverse wave at an antenna is rolling up to a standing wave, to a rolled up wave, and this has the properties of a scalar wave. You see that if you want to receive electromagnetic waves, then you need an antenna which has the length of half of the wavelength, you know. Mm-hmm. And if the received wave is reflected at the end of the antenna, is running back and is reflected again and running back, and by this it is rolling up, and we call this a standing wave. And this standing wave has the property that it is rolling up all around one field pointer, because the other field pointer, both field pointers are perpendicular to the direction of propagation. If you roll it up around one point, you may roll it up around the electric field pointer or all around the magnetic field pointer, and then it propagates in the direction of the other field pointer. That means that with this model, you have a vortex. You get a vortex, which is a rolled up transverse wave. And so it has to do one with the other, but this rolled up vortex is now propagating in the direction of a field pointer, and the field pointer oscillates, and that means these ring vortex oscillates as well. And if it is oscillating, then if it is in the region of the speed of light, then you know by the Lorentz construction of the theory of relativity, it is getting smaller, And if it's slower, it's getting bigger, and that means it changes the size. And if it is changing the size, this ring vortex is changing wavelength as well, because the vortex speed all around the ring is the speed of light, and this is constant. And this means that then the frequency is changing as well. And the change of frequency, this is what we are able to measure. And if you have always changing frequency, this is what we call noise in engineering, electrical engineering. And that means we are able to measure the scalar waves nowadays. But we measure only the summary of all these scalar wave effects, which are slower or quicker than the speed of light. Okay. And this mixture is in our ideas, in what we learn at school, at university, it is waste. You see, it is waste. If you have learned lessons in high frequency, you learn how to reduce these noise, because you learn that the useful signal has to be separated from the noise and has to be bigger than the noise, then you are able to receive it. What we do not know is that this noise may be used. It's very useful. It's not waste. What I do is that I design equipment where this scalar wave part is maximized and the Hertzian part is minimized. Just the opposite we learn.
Now, a few weeks ago, I had a researcher by the name of Joe Farrell on, and perhaps you heard of the Philadelphia experiment conducted back in the mid-40s. And he described this experiment as actually happening. It was a military research project. Conducted back, I think, in the early 40s of last century. And one of the descriptions of the phenomena that they observed is that, well, they conducted this experiment out at sea. And secondly, the effect that they observed is that the eyewitness of this experiment described the field as being a field within a field. So perhaps we have an electromagnetic field component here, transverse, but then we have this separate field component, which is this longitudinal or perhaps a scalar component, as being described as a field within a field.
I think this is a very bad example, because it was too speculative, this experiment. Tesla was the experimental leader, but he never opened his mouth and said nothing about this, because he don't want it to be brought into connection with this experiment. Because what he did is very different and is much better. This was the first step of the United States to go into the direction of scalar wave experiments, and I think it was more Hollywood number than it was reality, what they did at that time. So this is really a very bad example. But if you want to know what Tesla did, then you have to repeat his experiments, and then you have to find descriptions and explanations to his experiments. I think then you learn much more by using my experimental kit, perhaps.
So this kit is available from You have a store, or?
Yes, I have an institute, and this is called the First Transfer Center of Scalar Wave Technology. Formerly, it was a transfer center of a big foundation in Germany for drives, because I give lessons in drives and energy engineering as well. But now, I think it was 5 years ago, we changed the name and the subject, because we now want to develop these things. This is much more exciting than to do standard physics and standard technology.
Mm-hmm. How would people go about ordering this?
Yes, well, we have an account, www.etzs.de, ETZS for Erstes Transferzentrum, First Transfer Center in English, of Scalar Technology. Another possibility to go there is to use my account, www.meyl.eu is the English one, meyl.eu, and there you find it in English, and I think the shop is in English as well. So it is very easy to get this, and we send it directly from Germany, and with the American tension, 120 volt and so on, 60 hertz, so no problem. What I'm observing is that first we sold more in the German version, and now we nearly have only English deliveries. To the, yeah.
Okay, Dr. Meyl, we have a caller here, Harvey from Ohio. Bill, could you put Harvey on and ask a question?
Hello.
Harvey, are you there?
Oh, yeah,
Harvey?
I just got up for a second. Yeah, sure. Yeah, this
you
is
have a question for Dr. Meyl?
Yeah, could you ask him, has he seen any kind of effects with time distortion and the use of magnetic fields against each other at high frequency, like he's referring to as a scalar wave?
I've understand the question. No, in my opinion, the time is constant because we have selected what 1 second is, and I don't agree with the idea that the time would be influenced by experiments. You see that this problem occurs only by using the theory of relativity, which is using a constant speed, that is the speed of light. And the speed is measured by meter per second. That means if the meter changes, then the seconds have to change as well, and that means the clocks go wrong. Another possibility, and that is what I'm using in my theory, and that's why I'm able to calculate things others are not able to calculate, because I say that the time is constant. That means if the dimensions differ, then the speed is differing as well. That means it is another situation, and I call it a theory of objectivity.
Yes, I read that. Only one other further thing. I do work in Tesla coils also, Professor. And recently I'm holding a Teslathon in Ohio this next Friday. I just developed what is known as the alternator-powered Tesla coil, and I drive this at 456 hertz. Now, my question regarding this, what I was able to do is get to select a capacity that would resonate with the 456 hertz driving the pole pig transformer. Now, when this was done, I was able to increase my output voltage and my output amperage by 60%. So it was a great gain here. But when I scoped out the signals, I see that normally the 120-degree signals phasing from the alternator prior to testing of the load showed 120 degrees, but then when I drove it, it showed angle near 180 degrees. So couldn't this be considered a sort of a distortion of time versus what the machine is outputting timing-wise between the two waves and the phase angle change that occurs? I'm sorry, this might be a little too complex, but I just wanted to submit it for comment.
Yeah, I can't give a comment because I have to see it, what you have done. I have to not on the phone. It's impossible to explain.
Yes,
this.
Okay. I'll go then and let other callers.
Yes. I think the frequency is very low, and that means the coils have need to have huge dimensions. And well, I have no experiments done on this field. Sorry.
Mm-hmm. Now, Dr. Meyl, you said that you're using low voltage in your coil, or to drive your coil. You said it was only 10 volts, peak to peak.
Yes.
Okay.
And what we are doing is that we are able to drive a small boat with perhaps 4 watt in a pool. And perhaps you have seen it. I have shown it on a fair, and I want to show it next year in Mannheim in Germany on a fair as well. I'm invited to do this special show, to organize a special show on free energy and neutrino power. At this fair, I show as well this boat. And I think nearly 500,000 people will come and see.
Mm-hmm. Yes, I saw your lecture last year, and it was fascinating. People can go to my website under Tesla Tech 2007 and take a look at some pictures that I took at the conference of Dr. Meyl's lecture. And his demonstration of this fascinating technology, the scalar wave technology. Doctor, I'd like to thank you for coming on the show today. Mm-hmm. Do you have any lectures coming up or any conferences coming up very soon here?
Not in the States. Next week I will be to Budapest, and then 3 days later in Copenhagen in Denmark. And I have no plans for the States. Last year I had been on this conference you talked about. This was the Tesla conference in Salt Lake City, and I gave a lesson in California. And we have the idea to repeat this lesson, which will take 3 days, I think, in the region of San Francisco. But we have no exact date. Please have a look at my homepage, and there you will be informed about the next speeches and presentations.
Okay. Thank you very much, Dr. Meyl, for coming on the air today.
Thank you very much for calling.
Fascinating talk. Okay, that wraps up another hour of Progressive Technology Hour. I'm your host, Bill Alek. Coming up next is Michael Elajan.